Now we take the problem 86 of your textbook, and incidentally, this is the last problem of this chapter. This problem is very much similar to the earlier problem, problem 86, but the uh, author of this book, Professor Verma, has placed the problem in a different way. You see, it is the same solid sphere, and it is rotating in a clockwise direction with an angular velocity v by r, and its center of mass has a forward direction velocity of v. So, and it says with it collides it collides elastically with the fixed smooth vertical wall. That is only new thing in this question. So if we consider this as condition 1, condition 2 is it collides with the wall here. Collides with the wall here. This is condition. Find the speed of the sphere after it has started pure rolling in the backward direction. Okay, this is the collision. After collision, what will happen? Since it's the elastic collision, it will move backward. So let us say this is position 3. Position 3, when it is moving backward. Now, since it's an elastic collision, it had center of mass had a velocity v. So since it's an elastic collision, its center of mass will now have a backward velocity v. Now have a backward velocity v. And it is here also it was moving rotating in a clockwise direction. Here also it is rotating in a clockwise direction. At this point, at this juncture, that means at position 3, you find that the rotation and the linear motion are opposite to each other. That means the angular momentum created by them, they cancel each other. And if this angular momentum cancels each other after some time, fourth position will come when they will cancel each other and then it will start rotating in the opposite direction. So we go by this, that we write it this way. Find the speed of the sphere after it has started pure rolling. That means in the fourth position, we have to find out the answer. But let us consider the third position first, right? So we write about the third position, you can write situation 3. Situation 3. In situation 3, what happens? The sphere moves backward with a linear velocity v. The sphere moves backward with, let me write, same linear velocity v. Same linear velocity v. In bracket, we write, since the collision was elastic. since the collision was elastic. Since the collision was backward with a velocity, same velocity v, as shown in position 3. Here, the velocity v creates a anti-clockwise angular momentum. Because this is the radius r, let us say, and this velocity is v, this motion is in this direction, and the force acting behind it is mv multiplied by r, it creates a anti-clockwise angular momentum. And it is said in the question that this rotation is going to stop at some point. So definitely the reverse angular momentum created by v is more than the original angular momentum omega related to omega. So net angular momentum is equal to mvr minus I omega. This is equal to mvr minus I omega is given v by r. Even if it's not given, we know omega is v by r. Right? This is equal to mvr minus I is 2 by 5 mr square, 2 by 5 by 5 mr square multiplied by v by r. So this r and this r square gets cancelled. We are left with only one r. So on the this is equal to mvr minus 2 by 5 mvr. mvr is equal to 3 by 5 mvr. And let's write, the paper setter has not asked for it, but for our understanding, let's note that this angular momentum is anti-clockwise because we have taken mdr first. Anyway, that was not asked in the question. Right? Now, after some time, the pure rolling starts here. When pure rolling starts, its velocity, linear velocity backward, will be v1 here. And its angular velocity will be, let's say, omega 1. In between there was a point. We can draw here also. In between there was a point when it had only a linear velocity and no angular velocity. That means when the two angular momentums, initial angular momentums, J just cancelled each other. And because of this linear velocity has a torque, it will create a new angular velocity omega 1. So we write, when pure rolling starts, when pure rolling starts, say this is position 4, when just the two angular momentums cancel each other, say this is position 5, when pure rolling starts once again. So we can write C position situation 5. Situation 5. When pure rolling starts, then say its angular velocity is v1, omega 1, and linear velocity is v1. Say its angular velocity, which will be now anti-clockwise, is equal to v1, angular velocity v1, angular velocity is omega 1, its angular velocity is equal to omega 1, and linear velocity is equal to v1. Let us assume that. Once we have assumed that, then the resulting angular momentum, the resulting angular momentum is equal to then m, let me write it, take one line down. The resulting angular momentum is then m v1 r plus I omega 1 is equal to m v1 r plus, now it is plus because both are helping each other, both angular momentum due to rotation and angular momentum due to translation motion, both helping each other, is equal to I v1 r equal to, now I is equal to 2 by 5 mr square by 5 mr square. This 2 looks bad. 2 by 5 mr square into omega 1 is 1 divided by r. This r and r square gets cancelled. We are left with only 1 r. This is equal to mv1r plus 2 by 5 mv1r equal to 7 by 5 mv1r. 7 by 5 mv1r. So, this angular momentum cannot be created once again. So, in position 3, angular momentum was 3 by 5 mvr, and position 5, angular momentum is 7 by 5 mvr. These two has to be same. Conservation of angular momentum conservation of angular momentum 7 by 5 mv1r is equal to, earlier again angular momentum 3 by 5 mvr. It was 3 by 5 mvr. From here, m and r gets cancelled. M and R gets cancelled, AM R gets cancelled. So what we are left with, V1 is equal to, oh sorry, the 5 and 5 also gets cancelled. So what we are left with, V is equal to 3 by 7. So V is equal to 3 by 7, sorry, V1 is equal to 3 by 7 V. That is the answer they want you to find out. That means, I repeat once again, look at the picture. When this ball started here, it was a forward motion was V, and there was a angular motion also V equal to omega r, and then it ball went and hit the boundary wall somewhere here, is position 2, and since it was an elastic collision, the ball rebounced back with the same linear velocity, and then it's had a linear velocity and the angular motion, they were opposing each other. Anyway, we found out the angular velocity, net angular velocity. After some time, what happens in position 4, here the two angular momentum, they cancel each other, and momentarily it stops rolling but continues to move in backward direction. This backward velocity V1 creates a torque on it and starts rolling in the opposite direction. And this value V1 is equal to 3 by 7 of the original forward velocity V. Here your chapter of rotation is complete. Next day we shall start the next chapter. I think in your textbook, next chapter is gravitation.